Hello girls, this is part 2 of chapter 11, section 3, properties of waves. In this chapter, we started our discussion about types of waves. The first type was called transverse wave. Okay, now if you just make this pulse with this rope, we will call the shape formed pulse wave. If more pulses are created, we will call it periodic wave. They are not different types. It's just if you have a single pulse, we call it pulse wave. If you have more pulses generated, it's periodic wave that will take the following shape. Okay, so as a revision, this is the transverse wave with parts labeled as crest, trough, wavelength, the distance in between, and the amplitude. It's the distance between the equilibrium position and a lowest point, which is the trough, or the distance between the equilibrium position and the highest point, which is the crest. Now let's start discussing the second part of waves, which is longitudinal wave. Longitudinal wave, if you remember when we brought a slinky to the class, we started vibrating it on the ground by compressing part and releasing it. The compressed part, we call it compression. The stretched part here, you can call it rarefaction as well. Okay, so it takes place like this: a compression first, then a rarefaction, or the stretched part, compression, then rarefaction, and so. So for a longitudinal wave, you notice that the direction of the propagation of the wave is parallel to the direction of vibrations. Vibrations are taking place back and forth. Direction of propagation of the wave is similar back and forth, so they are parallel to each other. This is the main difference between longitudinal wave and transverse wave. Transverse wave, direction of propagation or the motion of the wave was perpendicular to the direction of the vibrations that were taking place up and down. Now, longitudinal wave, we will represent it on an XY coordinate system, but we cannot draw slinky on it. Okay, we need to have a mathematical representation or a mathematical function, which is one more time the sine curve. Okay, now each part where you have coils compressed or close together, you have greater density. Here you will have lower density of the coils. They are not having the same amount in the same space. So here you have greater density, here you have lower density, and so to represent the longitudinal wave, the x-axis will represent the equilibrium position one more time, and the y-axis will be represented by density. Okay, to show great density and least density. And here you can see that x1, x2, x3, and x4, they are representing, okay, a compression, then a rarefaction, a compression followed by a rarefaction. You can notice that x1 is having the highest point to represent the greatest density. x2 has the least point to represent the least density. After that, in this page, you will learn relationships among period, frequency, and wave speed. Let's recall the definitions of each. A period is the time required for one complete cycle to happen. Okay, time needed for a cycle. So it's technically time measured in seconds. Frequency is the inverse. Frequency is the number of waves that are taking place in 1 second. Yani, and here in this diagram, if I say this curve of or those vibrations are happening in 1 second, all what you need to do in order to know the frequency is to count the number of waves in the second. So let's count together. This is the first wave. A wave consists of a crest and a trough together. This is the second wave. This is a cycle. This is the second cycle. So we have 2 cycles in 1 second. That means they are or the frequency of this wave is 2 hertz. Now remember or recall the speed formula, which is displacement divided by time interval. Okay, in waves what matches displacement is the wavelength, because if you remember, the highest point or lowest point, this is technically displacement from the rest position. Delta t is represented by period. Okay, if you divide a wavelength by period, you will calculate the speed of the wave. Now you took this relationship before, which is frequency as the reciprocal of a period, or the inverse, or 1 divided by the period. You can substitute 1 over t with frequency according to this relation to get the final form of a speed wave, which is frequency multiplied by wavelength. Okay, this is the second speed of wave formula. Keep in mind that sound waves, they travel with the same speed, okay, in one medium or at a given medium. So the speed of a mechanical wave is constant for any given medium. That means whatever the sound source, okay, the sound produced by those sources will have the same speed regardless of the frequency or the wavelength of the source, because at the end they will be multiplied by each other. So if a source has greater frequency, it will have a low wavelength, to give the same product for one that has lower frequency but greater wavelength. Now in here you should know that you are required to read sample problem D, study it and solve questions 1, 2, 3 and 4 because they are highlighted. Finally, you should know that wave transfers energy. This is what a wave does, okay? And you should know that waves, they carry energy from one position to another, representing them by a specific amplitude. The greater the amplitude, like in here, okay, if you have another wave with a greater amplitude, that means it's carrying greater energy. If you want to understand this more, you can imagine water waves. Water waves with greater amplitude, they can carry greater energy. That's why they cause greater damages if they hit any coastal region. Okay, at the end you are required to highlight the book according to the highlighted parts here and to solve formative assessment questions as well. Thank you. Have a nice day.